Physics reaction video number 80. So interesting. This is AP Chapter 28, Photoelectric Effect. I think this was just posted in the last week or so, which is probably after the AP exam. So this might be like extra material or something. So that sounds exciting. Let's go.
What we're going to look at is we're going to look at the dual nature of light. But the first thing we're going to do, we're going to take a look at the particle nature of light. And what best explains the particle nature of light is the photoelectric effect. The photoelectric effect. The first hints about the photon or particle nature of light came with discovery that a negatively charged electroscope could be discharged by shining UV light on it. The emission of electrons from a substance due to light striking its surface is called the photoelectric effect.
Cool.
So you can see you've got a negatively charged electroscope, and if you shine UV light on it, electrons are ejected. So now it's not as you can discharge it. Now you can, in a sense, neutralize it. You can ground it just by shining UV light.
Cool.
All right, so here we have an apparatus.
So I was just thinking about this. If it's negatively charged, it should be slightly easier to pull these electrons off than if it was just a neutral metal. So I wonder about, this experiment. I mean, obviously it shows the photoelectric effect, no question about it, and I love this historical sort of approach. I guess I'm just thinking about what frequency it would take to do it. I would think you wouldn't need quite as energetic photons to get these electrons to jump off as it would take to get the next set of electrons to jump off, because they're binding energy, for lack of a better word. I don't like that energy. I don't like that word. Yeah, how well the sort of barrier for them to escape the metal has been lowered because there's just all these electrons around. But I guess I wouldn't know by how much. That's really interesting. I suppose you can measure that. Well, anyways, here we go.
And you can see the cathode is attached to the negative terminal. The anode here is attached to the positive terminal. Now, there's no connection between these two electrodes. So we have a window here. If we shine UV light through that window and it hits the cathode's going to emit electrons, and those electrons are going to move from cathode to anode. So we're actually going to have the electrons move in this direction, okay? Remember, conventional current will move in the positive to negative direction.
Damn you, Ben Franklin.
So if the light passing through the window hits the cathode with a certain threshold frequency, we'll say F sub naught, electrons will be emitted from the cathode and travel to the anode, producing a current.
Cool.
Characteristics of the photoelectric effect. The photoelectric effect has the following characteristics. The current is directly proportional to the light intensity. If the light intensity is doubled, the current also doubles.
Cool.
The current appears without delay when the light is applied. Electrons are emitted only if the light frequency F exceeds a threshold frequency.
So it's interesting, right? The first one would be explainable by lots of other models, not needing this sort of quantum nature. But the second and the third ones are just these weird things, right? So it's actually pretty cool when you're in the lab and you prove number two. It's like, boom, there it is. It's like, wow. There's not a matter of having to sort of wait until you've collected on average enough energy before you pop out. It's not like the electron is sitting there heating up, and then going, kind of like, I don't know, bubbles in boiling water or something. It's really that every once in a while, an electron absorbs a photon that has enough energy for it to escape. So 2 and 3 are really the new things. And in the lab, I think number 1 is certainly true and easily detectable in the lab. But it doesn't help distinguish between these multiple theories of what's going on. But 2 and 3 are the weird stuff. So very cool.
The value of the threshold frequency depends on the type of metal from which the cathode is made. So what I'm going to do, I'm going to end this part. I'm going to show you a PhET simulation
Cool.
to kind of show you that.
Awesome.
All right, so we have UV light hitting a piece of copper metal, okay? The copper over here is connected to the negative terminal of the battery. So that's going to be my cathode.
I really love how this simulation is sort of diagrammatically so similar to the other one that she used, which kind of makes sense, right? Because that other diagram is pretty common. And so when the FET folks put this together, they're like, okay, this is what people are used to seeing. Let's make sure have the light coming in at some funky angle. And let's have the battery be, kind of down here at the bottom. So that's really, really cool. And then, of course, we can just ramp up the frequency, or I guess ramp down the frequency and the intensity, and be able to see, and there's these little cartoons of what's happening and being able to measure the current. This is such a great simulation to help really drive this home.
Okay, and you can see that electrons are moving over to the anode. Now, if I were to change the intensity of the light, let's see what happens to the current. So as I increase the intensity, you can see that I'm going to get more electrons coming over from cathode to anode, and my current goes up. Okay, now we talked about a threshold.
So I was actually just looking over here at these check boxes. You can tell if you watch these things that some of these travel faster than others. And so this little checkbox is really, really telling when you think about some of the subtleties of this experiment, right? Because very, very often the calculation you're told to do when you're doing this sort of work function stuff with the photoelectric effect is really only predicting what the highest energy electrons, actually I guess it's going to be the lowest energy electrons, are going to achieve. So this is a really interesting checkbox. I think the rest of these are just different ways to sort of see the results. I'm curious to see if she plays with these checkboxes, but so far she's really been able to use this this diagram and this animation to really hit home the big ideas. This is very cool.
Threshold frequency. Well, let's see if I increase the wavelength. Remember, there's that inverse relationship between frequency and wavelength. Frequency times wavelength will equal the speed of light.
Sorry, I was just thinking a little bit more about this highest. I guess, yeah, the normal work function equation that I'm guessing we're going to see here in a little while is they are the highest energy electrons, right? And so only the highest energy electrons sort of follow the straightforward work function calculation that's going on, but there are lower electrons that can also absorb a photon, but they, by the time they escape, they don't have quite as much energy. And again, if you watch this video, you'll see some electrons pass other ones. Sorry, I just was thinking about that. Let me back up and listen again.
Between frequency and wavelength, frequency times wavelength will equal the speed of light. So if I were to increase the wavelength, I'm going to take us out of the UV and bring us into the visible spectrum. You don't see any electrons being emitted because there's a certain threshold frequency or wavelength, in a sense, where we're going to actually have the emission of the electrons. All right. So then the next part, if the potential difference, delta V, is more than about 1 volt positive, anode positive with respect to cathode, the current changes very little as delta V is increased. So we'll take a look to see if that's what happens. And if delta V is made negative, the anode negative with respect to the cathode, by reversing the battery, the current decreases until at some voltage, we're going to say negative V naught, the current reaches 0. The value of V naught is called the stopping potential. The value of V naught is the same for both weak light and intense light. A more intense light causes a larger current, but in both cases, the current ceases when delta V equals.
So I love this. I think number 5 is really, really subtle. So you may have seen me be sort of puzzled thinking about it, because in my brain, I was jumping to 6 and 7. I think 5 is very subtle. But I think 6 and 7 especially, is kind of the big take-home moment. So number 5, if the potential difference is more than about 1 volt positive, current changes very little. So are they saying that if it's less than a volt? I wonder if she's really going to address number 5. Because I'd like to see, because the problem is that I think that it's a subtlety that is important, But if 6 and 7 are your big ideas, I mean, I guess what they're saying is that the battery itself could be ripping out the electrons. Well, let's see how she does. Very cool.
Equals negative V naught. And this is violation of the wave theory of light. So that's what led us to believe that light also has particle nature. So according to the classical wave theory of light, the intensity of the light determines the amplitude of the wave. And so a greater light intensity should cause the electrons in the metal to oscillate more violently and to be ejected with a greater kinetic energy. But we don't see that when we've reached this stopping potential. All right, so I'm going to stop this. We're going to go back to the simulation. All right, so what we're going to do, now it said if the voltage was positive 1 or above, we're really not going to see, if we increase the voltage, we're not going to see a change in current. So let's see if that happens. So if I increase the voltage here, okay, we really don't see a change in current, okay? And then it said,
So, but it did look like the particles go faster, right? So they're ejected and then they're accelerated here. But if it's less than a volt, if it's less than a volt, a few of them might not make it. This is really interesting.
what if you decrease? Okay, we're going to change this voltage. We're going to make the voltage negative. Basically, we're going to flip the anode, the cathode here. So I'm going to bring this, I'm going to make it negative so that my current goes to 0, all right?
Cool.
Here's my current, it goes to 0. Now notice what happens. The electrons are coming over, but then they're kind of being pushed back, all right? And you know what? Let's see if anything happens if I change the intensity.
Cool.
So if I change the intensity,
you get more. Cool. A few of them are making it.
So we still have the electrons coming back, all right? And we don't change our current at all.
It's interesting that if it seems to me that if any make it, maybe this digit should be changing.
Okay. All right, so let's go back to the notes.
Very cool.
All right.
So she didn't really talk about number 5.
We saw if the potential difference is more than 1, we saw that increasing it doesn't change the current. We made delta V, we made it negative by reversing the battery, and the current decreases until at some voltage the current reaches 0. Cool. We're going to call the value V naught there, we're going to call that the stopping potential. And then the value of V naught is the same for both weak light and intense light. A more intense light causes a larger current, but in both cases the current ceases when that delta V is negative V naught.
One of the things I wonder is if you were to explain sort of the cathode, the anode, and the light mechanism, and then showed the controls of the PhET simulation, right? This is how you do intensity, this is how you change the battery, and this is what the animation means. And you ask students to just play around with it a little bit. Would they achieve all of this understanding? I think some would, right? And so maybe you would need some sort of group conversation. Ooh, I tried this. You guys, you should try this. Whereas what she's done here, she sort of jumped right to the pieces and parts that help this narrative. Because I always wonder whether students are like, oh, that's cool, I'm going to go play with that. And I guess my assumption is that they're only going to do that if they can have some incentive, like, hey, see if you can figure out some cool patterns and report back or something like that.
All right, so the photoelectric current dependence on the light frequency in the battery potential delta V. All right, so this is that threshold frequency. So no matter how weak the light, there is a current if that frequency is greater than that threshold frequency.
I'm not sure why this is tilted down. I mean, if you go higher frequency, I actually would have expected this to go up. Just a little bit, right? Because you can dig out some lower electrons. I'm not sure why it goes down. But obviously the point here is this huge difference, which is absolutely detectable in the lab if you've got the ability to change the frequency.
No matter how intense the light, there is no current if the frequency is going to be less than that threshold frequency. All right, and here we have A more intense light causes a larger current. We saw that. The weaker light, it wasn't as large. So the current, though, is independent of that change in voltage. All right, when that change in voltage is greater than or equal to 1 volt, we saw that there was really no change in current. But no current flows when delta V is less than that negative V naught or negative V stopping potential. The stop.
So here, she did a good job of sort of connecting to that point number 5, right? That there's really, it doesn't really sort of flatten out until you get above a volt. And that makes sense. Again, I think it's subtle. So I sort of like that she skipped out to here and skipped over to there and didn't really talk a ton about what's going on in here. Because this is really the driving home point. If we're talking about, this is the first time we're hearing about the particle nature of light, there's some subtlety here for sure. But man, this flat line here and this stopping point here are the really important points.
Potential is the same for intense light and weak light. Understanding the photoelectric effect. A minimum energy is needed to free an electron from a metal. To extract an electron, you need to increase its energy until its speed is fast enough to escape. The minimum energy, E naught, needed to free an electron is called the work function, or you might see it as W naught. So this textbook is using E naught. Some textbooks will use W naught as that work function. Remember, work is just a form of energy. So the work function of the metal. Now, on your AP reference tables, you're going to see the phi symbol for work function, but it's written off to the side.
That's funny.
All right, the work functions of some metals.
Whoa.
All right. So we were looking at copper. Copper has a work function of 4.65 electron volts. That would mean those electrons would need to have at least that amount of energy to overcome the work function, to overcome that threshold so that they can leave the copper metal surface. An electron with energy, E electron, inside a metal loses energy delta E as it escapes. So it emerges as an electron with kinetic energy. K is going to equal whatever that electron's energy was to begin with minus whatever that change is that allows it to escape. The work function energy, E naught, is the minimum energy needed to remove an electron. So the maximum possible kinetic energy of an ejected electron is going to be, K max is going to be whatever that energy that electron started with minus that work function energy, all right, E naught. We can use the conservation of energy to...
All right, I think I'm just going to pause right there. So really, really great stuff here, right? Especially the connection to the simulation, all the sort of relevant points, but really not getting caught up too much in some of the nuance, which is great, right? Because there's a big take-home moment that's trying to be made here. So I thought this was really great. I think that it sets up students well, especially if they're going to go play with the simulation at all, or maybe go into the lab, or ready to do some calculations to try to figure out, if something weird were happening in the lab, can we see if it's the photoelectric effect that might be explaining it? All right, everyone. Well, hey, have a great day. And remember, physics teachers are awesome.